Hi everyone, in this video we are going to solve the M1 mock paper 1. For those of you who are giving mocks under me, that is Edexcel, this will be the mock solution. So I'm going to take every question from that paper and solve it over here. So on this mock paper, they have 7 questions. I made a printing mistake, my like typing mistake. 1, 2, 3, 4, 5. This was question 7. All of a sudden, I forgot to input question 6. So if we skip question 6, we have 7 questions because this paper doesn't have question 6 over here. Okay, now again, we're going to start with the first question, obviously, question 1. This was from the kinematics. So let me just take this out of this file and then use it in my other page. So question 1 of our mock paper M1, it says that the diagram shows the velocity time graphs for the motion of two cyclists P and Q, who travel in the same direction along a straight path. Both cyclists start from red, that means the initial velocities are 0 at the same point O, and both accelerates at 2 meters per second to a velocity of 10. That means their acceleration was 2. We can clearly understand that by the inclination of these graphs, right? Both graphs for P and Q were inclined at the same angle. That means gradient for this velocity time graph must be same. And obviously for velocity time graph, gradient gives you acceleration. That's what it indicates. If the inclination for the two cyclists are equal, it indicates that the gradient for the two cyclists were also equal, which means that acceleration is equal for both P and Q. It was already stated over here that A was 2 meters per second. Okay. And now it says that both then continues at a constant speed of 10 meters per second. We can clearly see that. And it also says that Q starts his journey t seconds after P. P and Q didn't start from the very start of the journey. P started at exactly t equals to 0, and after some time, Q started the journey. Right? We can clearly see that Q started when time is equals to capital T seconds. And we need to show in a sketch of the diagram the region whose area represents the displacement of P from O, which was the origin, at the instant when Q starts. That means it wants you to find out that the distance traveled by P before Q started its journey, right? So in that case, this is how it will be. This is the point where Q starts its journey. So we're going to draw a straight line from here and just highlight the region over here. Right, this region or this area under the graph, always remember that velocity, for velocity time graph, area under the graph gives you the value for your displacement or distance, since over here the object was not changing any direction, right? So area under the graph will represent both distance or displacement because there was no direction changes involved in this part. So this one is for the displacement or distance traveled by cyclist P before Q started its journey. And this was it for the first mark. That is it. We just need to shape this region. Other than that, no other working is required. For part 2, like before we start with part, this actually typing mistake, maybe this is A, this is B. Right, for B part 1, we have a statement that given that P has traveled 16 meter at the instant when Q starts, that means this shaded region over here represents a distance of 16 meter, and using this value, they wanted to find out the value for T. Okay, now over here, we do not know what the final velocity of that object was at this point. We already know initial velocity was 0 because both the object starts from rest, right? It was already stated in the question. By this time, obviously time is capital T second for both the cyclists. Even though Q starts at T seconds, and by this time for P, it is also going to be capital T seconds. And the distance is given. We have also the value for your acceleration, right? Which is 2 meters per second over here. So okay. So as I was saying, so I'm going to use the equation for part B2. I'm going to write it very close to the graph, so it's quite easy for us to take informations from the graph. I already know that SP by this time, when time is equals to capital T second, has traveled 16 meter. I'm going to break down SP using an equation of S equals to UT plus half AT square. Okay, so it's going to be UT plus half AT square equals to 16. And obviously this ut is going to be 0 because the value of initial velocity was 0. This entire thing becomes 0. And now you have half, acceleration was 2, time was capital T square is equals to 16. These two gets cancelled out. T square, you just take this square to the right hand side. So it will be root over 16, which is eventually what? T is equals to 4 seconds, right? So when cyclist Q starts its journey, the time was 4 seconds for this entire graph. So I'm going to take this and write it over here. This was the working for part B1. And then again, after part B1, it says that the distance between P and Q when Q speed reaches 10 meters per second. Okay. They want you to find out that what was the difference in between the distance of the two cyclists when Q reaches this 10 meters per second speed. Okay, so we can also find that out. But again, we have to labelize the regions over here. For example, we're only trying to find out like this point of time. We have to find out this time when Q reaches the 10 meters per second speed. Okay, so as we were saying, wait 1 minute. Okay, yeah. Sorry, as we were saying that we need to find out that the distance for like at this point, right? For example, I'm going to consider this time as maybe capital T2. Okay, at this capital T2 time, what is the distance traveled by cyclist P, and then what is the distance traveled by cyclist Q, and what would be the differences in between their distances at this T2 time. But before that, we still need to find out this distance, right? We need to find out the area under this cyclist P graph, which is clearly a trapezium over here. So we can find this out, but we still need to find out this value over here because this trapezium will obviously have T2 and then this one, right? So we need to find out this value when P reaches the 10 meters per second. So I'm going to consider that as a value for TP, okay? Like this value on your graph is going to be TP. So TP represents when P reaches 10 meters per second. 10 meters per second. We can find this out because this was for clear and acceleration process, right? So we can use this T is equals to V minus U over A. I'm obviously using the equation V is equals to U plus ET. I just rearranged and made T the subject because I want to find out the value for your T. Right, so in this case, the value for T was represented with T subscript P, and V was 10 minus 0 over 2, which is 5 seconds. So this means that over here, this is 5 seconds. We also need to find out the value for TP, which can be easily calculated using the cyclist Q's information. So I'm just going to take this to the bottom because it's not needed anymore. This is the calculation for your B part 1, so B part 2. And we used informations of cyclists P so far over here. This is B part 1. And then again, we're going to find out the time taken for that T2. Like after, at the time when cyclist Q reaches that 10 meters per second, what was the value for time then? So I represented that as T2, which is time when ten meters per second, which will be again T is equals to V minus U divided by what? Divided by acceleration. So this is T2. Final velocity of cyclist Q was also 10. Initial velocity was 0. And acceleration was also 2. So it is again 5 seconds. The problem is T2, this one only gives you the value for the acceleration process. But on your graphs, right, the graph doesn't start from exactly T. The graphs from T equals to 0. So for T2, you also have to add this value from 0 to T, which was already 4 seconds. We calculated that in part B1. Right, so for T2, it will be added with that extra 4 seconds. So from T to T1, T2, Like this distance over here, like this portion of time was 5 seconds, and before that it was already 4 seconds delayed, right? So in that case, from the origin to the T2 point, the total time would be 4 plus 5, so 9 seconds in that case. So I'm going to write this as this plus 4 seconds, this plus 4 seconds, and eventually it's just going to be 9 for us. 9 seconds. Again, we're not trying to focus on the value for the time. We had to find out the value for your difference in distances, right? So in that case, we're going to use this part as over here. I'm going to first find out the area of the cyclist P graph, which is clearly a trapezium. I'm going to find out, sorry. I'm going to find out this entire area, right, which is clearly a trapezium. Maximum height is 10, parallel sides are 9 and 5, right, between, not 5, if this is 5, that will 9, this is 4. This portion from TP to T2, this is 4 seconds, and height was already 10 I've provided. So we're going to write that SP was, we're just going to use the formula for your trapezium, which is half total base was 0 to T2, which was 9 seconds, plus that above part, which was 4 seconds. I already said that this is like what? T2 minus TP, which is 9 minus 5, so which is eventually 4 seconds. Plus 4 multiplied with height was 10. And if you just cancel this out, this is 5. 9 plus 4 was 13. 13 multiplied with 5 is 65 meters. This is 65 meters. The distance traveled by cyclist P during that total 9 seconds, by the time Q reaches the 10 meters per second, is 65 meters. And then again, we need to do the same working for cyclist P or Q also. So for cyclist Q, it's quite easy. We can clearly see it just creates a triangle, right angle triangle. That would be half. That would be half base into height. Base is this. This is what 5 over here from T to T. From this portion to T2, this was 5 seconds. Height is 10, so it's just going to be half 5 multiplied with 10, which is 25 meter. We want to find out the difference in between the distances of the two cyclists when Q reaches that 10 meters per second, right? So you just want to find out the difference between these two distances. So I'm going to write just distance over here, which is 65 minus 25. 65, 25, this is 40 meters. Right, so this is a final value that you are asked to calculate over here. You want to find out the difference in between their distances by the time Q reaches the 10 meters per second. Right, this is the final working done. I hope it was clear for all of you. For part B1, there was no working. For part A also, there was no much working. But for part B2, it was a little lengthy. Right. Yeah, that's it then. We are done with our first question from the mock paper M1 mock 1. We're going to move on to the next mock question. Okay, this is your second question. This is, I think, about components and angle creating. It says that a light inextensible string. Always remember that light inextensible string indicates that overall the strings does not have any weight, and inextensible means that tension along all the way, or tension along all this length, throughout this entire length of the string, is going to remain equal. That means it doesn't indicate that tension over here is, if it is like 54, in this case it's going to be 25, right? Tension along the entire string is going to be of equal magnitude. That's what it indicates about inextensible. And light means that we're not going to take consideration about the weight of the string into our calculation. Okay, now it says that it has fixed, string has its ends attached to two fixed points A and B, and with A vertically above B, a smooth ring, like a smooth ring of mass 0.8 kg, 0.8 kg is threaded on the string and is pulled by a horizontal force of magnitude x newtons. The sections AR and BR of the string make angles 50 and 20 degrees respectively with the horizontal as shown in the diagram. The ring rests in equilibrium, which means that at the end, all the forces are balanced, right? There is no motion, there is no acceleration for the ring. And with the string taut, find the tension in the strings and the value of x. Over here, inextensible over here was the indication that tension along all the way was always equal. Or in this case, tension was only acting in these two directions, which is over here and over here. Right, these are the only two positions where tension was acting, and tension on these two positions at BR and AR is equal. So over here, every point is just going to be T. It's not T1 and T2 separate tensions. It's equal tension along the entire string. And we need to find out the value for x, but before that, we need to find the value for the string. In order to find the value for that tension of the string, we need to first divide the components of every part. So we will do that first. I'll obviously draw the vertical axis and horizontal axis. This time the vertical axis is going to be exactly on the vertical axis because it doesn't have an inclined plane over here, right? So it's just going to be totally vertical axis on the vertical axis. And wait, let me just create the angles over here. If it was creating 50 degrees with the horizontal over here, it is going to create 50 degrees with the horizontal using that alternate segment theorem. Right, and in this case, if it was creating 20 degrees with the horizontal, so this portion would be 20 degrees. Now this is T, and it will be on the vertical part, it's going to be T sine 50 degree because it was not creating angle with this vertical axis. This T with the AR was creating angle with the horizontal axis, so that's what it is going to have a T cos component for the horizontal axis. And then same again over here, this was also T. This T for the DR string was also creating angle with the horizontal. So it's going to be T cos 20 degree with the horizontal axis. And for the vertical axis, it's going to be T sine 20 degree. Now you already know that the entire ring was in equilibrium in all directions, in all planes. One is in the vertical plane and also in the horizontal plane. So over here, there will be no accelerations in any plane, not in the vertical but in the horizontal. A would be 0 for the vertical plane, A would be 0 for the horizontal plane. So in this situation, I'm going to arrange equations in terms of A for usually the vertical, not because the horizontal, because horizontal already have this unknown variable x, right? So I cannot obviously find out the value for your t using the unknown variable x. So we'll start with the horizontal axis. For part 1, so I will start with the vertical axis. Because on a horizontal axis, we have this unknown variable of x Newton. So resolving vertically, we're going to write with the equation resultant force goes to mass acceleration. Obviously, RF indicates resultant force, not reaction force. Now, resultant force is equals to MA. I'm going to consider the top one as positive. So it's going to be T sine 50 minus T sine 20 degree is equals to Wait, another thing, I forgot to input the weight over here. Obviously, the weight was 0.8 kg. So in this situation, it's going to have 0.8 g in the downward direction also. So this minus 0.8 g is equals to whatever that mass is, doesn't matter because you're going to um, have the value for your acceleration as 0, right? So 0.8 multiplied with 0 will eventually be 0. So there's no point of writing anything on the right hand side of the equation. So I'm just going to write 0 over here. So in that case, now you have t sine 50 minus sine 20 degrees. And I'm just going to take this 0.8 to the right hand side. So it's just going to be positive over here, 0.8. So in that case, t is 0.8. Obviously, the value for g in your M1 is 9.81, 9.8, not 9.81. That is for physics. For M1, we're going to use sine. So the value for your G as 9.8. So sine 50 minus sine 20. which is 18.4895, a very big value. I'm going to write 18.4895 Newton over here, but for the final answer, I'm just going to write 18.5 Newton. Okay. And again, after this, I'm going to write. So this was the working for your part one, right? And then again, using the value for t, you have to find the value for your x also. So for part 2, x is already obviously in the horizontal plane, right? So we're only going to use the horizontal plane over here. We're not going to work anything with the vertical plane. So we are going to write resolving horizontally. Again, I'm going to use resultant force is equals to mass acceleration, and acceleration over here is also 0. So in this case, resultant force is x on the right hand side. On the left hand side, you have t cos 50 and t cos 20. So I'm just going to write t. So x t cos 50 and t cos 20 is equals to 0. In that case, the value for x is t cos 50 plus cos 20, and obviously the value for your t was 18.5 or approximately like that, right? So I'm just going to multiply that cos 50 and cos 20 with that 18.5 value. So it's just going to be this multiplied with cos 50 plus cos 20, and you approximately get 29.259 something. So I'm just going to write it as value for x is 29.3 Newton. Right, this is the final value for your x with which that ring was held in equilibrium. And that was the working for your part 2. I hope it was clear for all of you to understand. So we're going to move to question 3 quickly. Now over here, it is about inclined components of forces. Again, we have to draw the planes of vertical and horizontal, but this time is just different because it is on an inclined plane this time. Previously, it was on a horizontal plane or on a horizontal axis, right? So question 2 and question 3 are quite similar. Now, in question 3, it says that a force whose direction is upwards, parallel to the line of the greatest slope of the line of the plane inclined at 35 degrees to the horizontal, acts on a box of mass 15 kg, which is at rest on the plane. At rest means that there is no acceleration, right? The value here is 0. And the normal component of the contact force on the box has magnitude r newtons. You need to represent that the value for your r is 1, 2, 3. The value for r is only 1 to 3 if you're going to use the value for your acceleration or like the weight component, like the g over here. If you're going to consider the value for g as 10, only then you get this value, right? So problem is that obviously in our cases, we're not going to use the value for g as 10. So I'm not going to get exactly this value, but my value will be close to 120 because I'm going to use a value for g is 9.8, because in M1, always remember, you are supposed to use a value for g as 9.8, not 10, not 9.81. Okay, so let me just write it down over here. This is wrong. This is also wrong. Only this one is correct. Value for g is always supposed to be 9.8, not 9.81 or 10. Now over here, I'm going to write, I'll first draw the components for this figure 1. Obviously, as my object is on an inclined plane, my vertical plane should always be perpendicular with that inclined plane, right? It is not always vertical to the horizontal ground. Vertical plane indicates that whatever plane your object is on, your vertical plane should be it should be perpendicular to that inclined plane, right? And parallel and horizontal plane should be parallel with that inclined plane. Okay, now over here, weight was acting from the center. Weight always represents, like, weight always acts vertically downward. There's no compromise for weight. Doesn't matter at what inclination you are at, weight will always act vertically downward. So over here, the weight was 15 g. And obviously, we all know that the inclination between the horizontal plane and that inclined plane, whatever the angle is, right? This is 35 degree. In that case, this component, like the angle between the weight and the vertical plane. Weight and the vertical plane is always equal to the horizontal plane and the inclined plane. So if this is creating 35 degree, this portion over here is also going to be 35 degrees. So in that case, if this is 35 degree, it is the vertical plane, the downward vertical plane will be 15g cos 35 degree, and the horizontal plane will be 15g sine 35 degrees. Above that, we obviously have this value for r, and there was a force over here, right? A force whose direction is upward parallel to the line of greatest slope and parallel inclined. Yeah, there was a value for force. Now we are not sure what the value for force was, but there was something. And it didn't mention anything about friction also, but we're not actually concerned about the horizontal forces acting on that box, because in part 1, they only wanted to find out the value for your reaction force, which can be only calculated by focusing on the vertical planes only. So there's no point of focusing on if this has friction or not. So for part 1 over here, I'm just going to resolve vertical forces, not anything involved with the horizontal forces. So resolving vertically, for a vertical portion, we have again resultant force equals to 0, because acceleration object was not accelerating vertically, right? It might be moving up along the plane, but it was not moving vertically over here. It was always connected and moving along the horizontal line. So there was no motion in the vertical plane. So that's why A is 0 for the vertical motion. And again over here, Newton. That is the final value for your reaction force of a part 1. This is it. Okay. Now again for part 2, it has two separate diagrams, right? And in the two separate diagrams, there were separate forces acting along the plane. And because of the separate forces, the object was moving either down the plane or up the plane. For example, I'm going to consider this as part A, like figure 2 part A, and this is figure 2 part B. For figure 2 part A, the object was about to move down the plane, right? Motion was down the plane. And for part 2B, the object was about to move up the plane. Motion was above the plane. And obviously over here, it was about to move, right? Maybe it was stated somewhere when the force parallel to the plane acting on the box is magnitude x Newton, the box was about to move down the plane. About to means that the value of your acceleration is still 0, but it's about to move downward, right? In that case, friction is going to move against the motion in the upward direction for figure 2A. And when the force has magnitude 5 newtons, 5x newtons, the box is about to move up the plane. So for 2B, the box was about to move up the plane. In that case, friction was about to move, about to act against the motion. In that case, friction was about to act down the plane for this part 2B, even though acceleration is still 0 for both the cases, right? So I'm going to write, like, I'm obviously going to draw components over here first. For all the cases, the weight is always 15 multiplied with 9.8, right? So from the center in the downward direction, we have 15g, and over here also we have 15g. And obviously, the weight and the vertical component is always going to create that 35 degree, because the plane was also creating that 35 degree with the horizontal plane. Okay, then let's just distribute the forces. In the vertically downward, it is still going to be 15g cos 35, which means the value for your r is still what we calculated in part 1, which was 120.4. Again, over here, we are trying to find out the value for your x Newton and also the component of the friction between the box and the plane. Always remember that friction is always calculated using this formula. Friction is equals to mu r, right, which is the coefficient of friction, and coefficient of friction between the box and the plane is mu, and r is the reaction force. So for this part, they are only trying to find out the value for your mu. They're only asking you to calculate the value for mu, because r was already calculated in part 1, which was 120.4, according to the calculation we got with using the value for g as 9.8 instead of 10, right? Okay, so this is 15 point G. In this case, the box was about to move down, right? In that case, friction is going to act in this direction, mu r. And over here, we're going to have 15 sine 35 degree. And over here also on the downward direction, we have 15 G cos 35. That means reaction force for both the cases, 2A and 2B, is just going to 20.4. And it was about to move up the plane. So 15 G sine 35 degree over here. And also this time friction is going to act down the plane against the motion, obviously. As we're trying to find out the value for x and friction, which are obviously combined on the horizontal motion of the journey for the two diagrams. So we're just going to resolve the horizontal motion for the diagram 2A and 2B only. So I'm going to write, like for this case, this is part 2, figure 2A, which is about the first diagram where the object was about to move down the plane. So for this case, I'm going to work with resolving horizontally. Resolving horizontally, obviously RF is equals to 0, because the object was about to move, it was not moving yet. So that means the acceleration is still 0. In that case, in the in direction to the motion was only 15g sine 35, and x and friction were all acting against the motion, right? So we're going to write 15g sine 35 degree minus x minus mu. R was, we already calculated. I'm not going to use exactly 20.4, because 20.4 was not the actual value, it was a continuous value. The actual value was 15g cos 35. So I'm going to calculate, like use the value for r as 15g cos 35 and carry it for the next portions. So over here I'm going to write mu 15g cos 35 degree. Right. Now, I'm going to make x the subject of this formula. This is obviously equals to 0, which is x is equals to 15g sine 35 degree minus, minus 15g mu cos 35 degree. Okay, now this is like an expression for the first value, where you got a value for x, like an expression for x, right? So this is like a first equation for x that you got. So I'm going to consider this as equation 1. And then again, I'm going to do the same calculation for that figure part 2b using the second diagram. So this is going to be from figure 2b. And over here also we're going to start resolving horizontally, because again vertically we're not involved with vertically because we already have the value for r. So resolving horizontally, this time towards the motion is acting 5x and against the motion is 15g sine 35 and that friction. So we're going to write obviously resultant force equals to 0. Over here it's going to be 5x minus 15g cos, so 15g sine 35 degree minus 15g mu cos 35 degree is equals to 0. And from here I can just make x the subject, which is going to be 15g sine 35 degree and 15g mu cos 35 degree divided by, so this will be positive on the other hand side, right? Yeah. This will be divided by 5. And this is like an expression for your x, the second expression for your x. And this will be substitute equation 1 into 2. So after this, I'll just carry out the working from here. Substitute 1 into 2. So if I'm going to substitute equation 1 into 2, it's just going to be 15g sine 35 degree minus 15g mu cos 35 degree over, this is equals to 15g sine 35 degree plus 15g mu cos 35 degree, and this entire thing is divided by 5. And I'm obviously going to take that 5 from the right hand side to the left hand side. So everything on the left hand side will be multiplied with 5. So 15 multiplied with 5 becomes 75. So this is 75g sine 35 degree minus, this is again going to be 75g mu cos 35 degree and 15g sine 35 and 15g mu cos 35. Okay, now I'm obviously going to take every mu together and every 15g sine, like sine 35 together. So it's just going to be minus 75g mu cos 35 degree minus 15g mu cos 35 degree is equals to 15g sine 35 plus 75g sine 35. Okay, and then again I'm just going to take, if I'm going to take just mu, the subject of this, and take everything to the right hand side, it will be 15. I can actually add up this 15g and 75, right? So 15 plus 75 is actually 90g. So this is 90g sine 35 degree. And again, I can add up the 75 and 15, which is again going to be what? 90g cos 35. Wait 1 minute. Wait, I was supposed to take this to the right hand side, so this is supposed to be negative. So 15 minus 75, 15 minus 75 was actually supposed to be negative 60, right? In that case, the negatives gets balanced out. So now you have 69.8 multiplied with sine 35 divided by 90 multiplied with 9.8 multiplied with cos 35, which is basically 0.4668. So you can just write 467 over here. Okay, the value for your mu is 467. Using the value for your mu, you can input this into that any of the equations, either equation 1 or 2, to calculate the value for your x, right? Which is obviously easy. I'm just going to substitute the value for mu into equation 1. So I'm going to write substitute mu is equals to 0.467 into equation 1, which was x is equals to 15g sine 35 degree minus 15g. The value for mu was 0.467. This is multiplied with cos 35 degrees. Okay, now which is 15 multiplied with 9.8 sine 35 minus 15, 9.8, 0.467 multiplied with cos 35. Which is approximately 28.1 degrees over here. So not degree, 28.1 Newton for the value for x. We can also write 28.08 or 28, just also is fine. Okay. Now this was the working for your question 3 for all parts 1 and 2. Right? Yeah, for all parts 1 and 2, right? Part 2 was lengthy, other than that, part 1 was obviously quite easy, right? We just had to calculate the value for your reaction force. Okay, so we are done with part for question 3. We're going to move to question 4. This is question 4. This is question 4. Okay. Now it says that a fixed wedge has two planed faces, each inclined at 30 degrees to the horizontal, and two faces, so two particles A and B of masses 3m and m respectively are attached to the ends at light inextensible string. Again, light inextensible string indicates that tension along the entire string is equal. That means tension over here and tension over here is equal, and light means that we're not going to consider the weight of the string as a part of our calculation. Okay. Now, after that, it says that each particle moves on the plane faces of the wedge. The string passes over a small, smooth light pulley. Small, smooth light pulley means that the pulley doesn't have any weight, and the pulley doesn't also create any friction. Okay. And right, fixed at the top of the wedge. The face on which A moves is smooth. Over here, this is smooth, no friction. And the face on which B moves is rough. So for part B, this face has friction, this face doesn't have friction. It also says that the coefficient of friction between the particle B and this face is considered as P. Like we usually consider the coefficient of friction as mu, but this is different. They're considering the coefficient of friction as P. Particle A is held at rest with the string taut. The string lies in the same vertical plane as lines of greatest slope of each plane face of the wedge as shown in the figure 3. The particles are released at rest. That means initially they will have zero velocity and they start to move. Particle A moves downwards and B moves upwards. Okay, so A moves downwards and B moves upward, and this doesn't have any friction and this does have friction. And the accelerations of both A and B each have magnitude g. Okay. Okay, so as I was saying that they both are going to accelerate with a magnitude of g, which is again what? Um, 9.8, right? 9.8 for our consideration. So we have to, for part A, it says that by considering the motion of A, find in terms of M and G the tension in the string. Okay. So for only for part A, let's just distribute the forces already. Like, and then we will start solving for part A separately, for part B separately. As I've already stated previously, that the vertical plane should always be perpendicular to the surface the object is on, right? It should never be perpendicular to the horizontal surface. If your object is on an inclined plane, your vertical plane should also be perpendicular to that inclined plane, not to the horizontal plane. They were all creating 30 degrees, so weight with the vertical plane will also create 30 degrees. Over here, it's going to have a weight of 3 mg, and it's going to create 3 mg cos 30 degrees. And on the upward, it's r. This is 3 mg sine 30 degrees, and this is the value for your t. Right. Other than that, it doesn't have any other forces acting on particle A because it was on a smooth plane. For particle B, it would be different. For particle B, it has a weight of just mg, and on the downward force, it says will be mg cos 30. I do not have space, so I'll just write mg cos 30 degrees, right? And this is for this part. And on the downward plane, is going to be mg sine 30 degrees. On the upward plane, we have reaction force. Over here, we have tension. As in this case, the object was moving down the plane, acceleration was g. And over here, the object was moving up the plane, acceleration was g again. As it was moving up the plane, acceleration, in this case, friction should be against the motion, right? So in this direction, friction should be, always remember friction was coefficient of friction multiplied with reaction force, right? So in this case, coefficient of friction was P, so it is going to be PR over here. Right, we have distributed all the forces for particle A and B. Now for part A, we only want to focus on particle A, and we want to find out the tension in terms of M and G. Okay, so for tension, obviously we're going to consider only on the horizontal forces because tension is on the horizontal plane over here. So in that case, for part A, the object was about to move down the plane. That means that weight component 15, like 3 mg sine 30 was greater than tension. That's why the object was about to move down the plane for that particle A. So we are going to write, focusing on particle A, obviously resolving horizontally. Resultant force, mass acceleration. Acceleration was also g in this case. So 3 mg, of course, it's sine 30 degrees minus tension is equals to MA was 3 mg again. So if you're just going to take T the section, section subject of this equation, this is going to be 3 mg. Wait, this was about to move down the plane, right? So 3 mg sine 30 minus tension. Let's take this and this becomes negative. Sine 30 is half multiplied with 3 is 1.5. The value for your t comes negative over here. 1 minute. Right. I actually forgot there was another typing mistake. The value for your acceleration over here was actually 0.1 g. Right. So in that case, there will be changes. It's just the value for your acceleration is going to be 0.1 g, 0.1 g. Okay. Now over here, we are going to calculate again. It is going to be sine 30. Sine 30 is actually half. Sine 30 is, wait, sine 30 is actually half. So we're going to directly write 0.5, and this value for g is going to be 0.1 g over here. So let me just correct it also. Which is 0.3 g, 3 mg at the end, right? So which is 1.5 minus 0.3, which is 1.2 mg. So the value for your tension in this case is going to be just 1.2 mg. Okay, now that was it for the working of part A. We're going to move to part B. By considering the motion of particle B, we will find out the value for B. Okay, we can obviously calculate that since now we have the value for tension and everything is available. For the value for P, we also need to find out the value for R, which is the reaction force, which is obviously equal to that mg cos 30 degrees. So for part B, let's start part B over here. We are focusing on particle B. For particle B, obviously, we are now first focusing on that vertical forces in order to find out the value for your reaction force. So resolving vertically, resultant force is still zero as the object was still not in motion in the vertical plane also. So reaction force minus mg cos 30 degrees is equals to 0. In that case, we obviously we understood the value for your R would be mg cos 30 degrees. Right. So yeah, that is it for part B. Like first part, we're going to move on to the second part of part B. Now over here for second part of part B, we're going to consider resolving horizontally. For resolving horizontally, we can write resultant force is equals to 0. Resultant force is equals to 0. And for part B, the distributions would be T minus friction and mg sine 30, because over here the object was about to move up the plane, so tension should be greater than all the downward forces. So T minus PR was your reaction for friction, and mg sine 30. This is equals to m 0.1 g, right? This was the value for your acceleration. Wait, right, sorry. This is not supposed to be, this is going to be m 0.1 g, because the object has acceleration down the plane, right? Or horizontally over here. So in that case, I'm only going to make E the subject of this equation, but the value for T was 1.2 mg. The value for R was mg cos 30. Cos 30 is root 3 by 2 mg. Okay, so you can just write minus root 3 by 2p. This is 0.5 mg and this is 0.1 mg. So I'm just going to take all the mg's together, which is eventually what? 1.5 minus 0.5. Anyways, it's going to be 1.2 minus 0.5. This is going to be 0.7. 0.7, so it's going to be root 3 over 2p, and then we're going to take this 0.7 to the other hand side. So it's 0.1 minus 0.7, which is 0.6. So p would be minus 0.6 minus root 3 over 2. The final answer over here is 2 root 3 by 2. The value for p is 2 root 3 by 5, or you can keep this into decimal, which is 0.693 also. 0.693. That is also an accepted value. Okay. Now, part B is done. For part C, says that find the resultant force exerted by the string on the pulley, giving its magnitude and direction. Okay. We have the value for the friction and tension, right? Again, the resultant force exerted by the string on the pulley also has to be calculated in terms of mg, because we haven't like been provided anything with the value for m over here, right? So the resultant force exerted by the string on the pulley will again be in terms of mg. For the direction part, they want you to find out the value for your angle that force is going to create with any of the plane. So in this case, if we focus the tensions according to the pulley, right? If I'm going to draw it over here, like this is your pulley, and from this part, there was a string attached to particle A on this direction and string attached to particle B on this direction. So there was a force of tension, there was a force of tension, and obviously tension is not going to act. Wait, let me just draw the diagram over here entirely. Now, if I'm going to draw a diagram over here, for example, this is 90 degree, this was 30 degrees, this is 60 degrees, right? This is also 30 degrees, and which means that this is also 30 degrees, 60 degrees. You can use that sum of triangle over here, 180 minus So 180 minus 30 minus 90 is always going to create 60 degrees. So tension over here was always creating 60 degrees with the vertical. If I'm going to draw components in this case, right, this tension in the downward direction is going to create T cos 60 degree, and this tension is also going to create T cos 60 degrees. So on the pulley, there's a downward force acting of 2T cos 60 degree, right? Because there are T cos 60 degree plus T cos 60 degree. At the end of the day, it's obviously going to add up together. So in that case, resultant force over here is going to be T cos 60 plus T cos 60. The value for T was again 1.2 mg. So you can write 2T cos 60 degrees and 2 multiplied with 1.2 mg and then cos 60. I think cos 60 is again half. Cos 60 is, yeah, half. So obviously this cos 60 and 2 gets cancelled out, and then the resultant force on the pulley is also 1.2 mg. Another thing is that were asking you to find out the direction. I actually made a mistake. For physics, you were supposed to calculate the angle in order to find out the direction. For M1, we just wanted to find out that in which direction the force on the pulley was acting. It was acting in the downward direction, right? So no need to calculate angle over here. We would just say that this much amount of force was acting on the pulley in the downward direction. So the direction would be downward. Just writing downward will give you the mark for this part. The diagram is certainly optional, but the working is obviously required. So yeah, this was the working for question 4. I hope it was clear for all of you. Moving to question 5. This is about moment. Okay. Okay, so question 6. Over here, it says that a beam AB supported by two vertical ropes, which are attached to the beam at points P and Q, where AP is 0.3 and BQ is 0.3. So AP is 0.3 and BQ is also 0.3. And the beam is modeled as a uniform rod. Uniform rod means that the weight of the rod must act from the center. That's what it indicates about the uniform rod. The entire length of the rod is 2 meters and mass of the rod itself is 20 kg. The ropes are modeled as light inextensible string. That means tension along the entire rope will be equal, and the weight of the ropes are not taken into considerations. A gymnast of mass 50 g hangs on the beam at point between P and Q. The gymnast is modeled as a particle attached to the beam at the point X, where Px is x meters and x should be greater than 0 or less than 1.4. And as shown in the diagram above, the beam rests in equilibrium. Equilibrium means at the end of the day, the total clockwise moment is supposed to be equal to the total anti-clockwise moment. There was no overall rotation like that, and the entire beam was not tilting from any angle. And for part A, it says that show that the tension in the rope attached to the beam at point P is this much. Okay. Tension in the rope attached to the point P. If you're only focused on finding out the tension at point P, then we have to take the moment from point Q. So let's just first distribute the forces. In the downward direction, we're going to have 50 g. Exactly from the center, we are going to have 20 g. Right, from this direction, we're going to have TP, tension at point P, and this part, we're going to have TQ, tension at point Q. Right. Other than that, there was no forces acting on this beam. So if I'm going to consider, like if I'm going to consider taking moment from point Q, in that case, this TQ will already cancel out, because if I'm considering this as your point of pivot, there is no distance between this TQ from this pivot point, right? If the distance is zero, so obviously moment at that point is going to be zero. So we're only going to consider the value for weight, gymnast, and this tension. If I'm going to consider the moment from this point, in that case, this will make the beam move anti-clockwise. This will also make the beam move anti-clockwise. This will make the beam move clockwise, right? From point P to Q, the length is 1.4, because entire 2 minus 0.3, 0.3, this distance is 1.4. Let me write it down. This distance is 1.4. Right. And from point Q also, another distance has to be measured, which is from the gymnast, which is going to be 1.4 minus x meter, right? And another distance has to be measured from the center to the point Q, which is going to be 0.6. Why? Because the weight acts from the center, right? The total length was 2. So this was exactly at the center. That means over here, each side is 1 meter. So if this from the center to the point B, if this was 1 meter and you have to subtract 0.3, that will give you the value from your point P, from point Q to the center, which is going to be 1 minus 0.3, which is 0.7 meter. Okay. Now using this length, you can find out the value for TP. We're going to start with part A as sum of clockwise moment. Sorry, equals to sum of sum of anti-clockwise moment. For sum of clockwise moment, that was only that TP. And again, I'm considering taking moment about point Q, right? So we have to write that taking moment about point Q. We can also write this taking M about point Q. So for that tension at P, this was 1.4 meters away. And again, we have this 50G gymnast, which was at 1.4 minus X meters away, plus 20G multiplied with 0.7. Okay. Now in that case, TP is going to be 50G multiplied with 1.4 is 50 multiplied with 1.4 is 70G minus 50Gx plus 20 minus, sorry, multiplied with 0.7 is 14G. This entire thing will be divided by 1.4. Now 70 plus 14 is 84. This separately divided by 1.4 gives you 60G. So this is 60G, and that 50 divided by 1.4 gives you 37 point, like it's a rough fraction value, 250 over 7 gx. And I'm going to break down that value for g. G was 9.8, so 9.8 multiplied with 60 is exactly 588, and that 250 over 7 multiplied with 9.8 is also exactly 350x. Right, this was exactly in the form your question asked you to keep your answer in. So tension at point P, we refer to that as TP, was exactly in the form 588 minus 350x. Okay, so this is it for part A. For part B, it says that in terms of x, find the tension in the rope attached to the beam at point Q. So if you're trying to find out the value for TQ, in that case, I'm going to consider taking the moment from point P. In that case, all the lengths should be also taken from point P. So which would be from this point P to the gymnast was already x. From point P to Q was 1.4, and from P to the center is again going to be 0.7, right? And these downward forces will make the beam move in the anti-clockwise way, and this tension at point Q will make the move in these downward forces now will make the beam move in clockwise way, and the tension at point Q will make the beam move in anti-clockwise. So we're just going to write these values and find out an again expression for TQ in terms of x. So for part B, we're going to take moment about point P, which is going to be sum of mm, anticlockwise moment is equals to sum of clockwise moment. In the anticlockwise moment, you have this TQ multiplied with 1.4, and that sum of clockwise moment, you have this 50G multiplied with 1.4 plus 20G multiplied with 0.7, which is the value for TQ is 50G with 1.4 is 70G, again 70G. Wait, sorry, this is not x, 1.4. As you're taking moment from point P, the distance should be x. So it's going to be just 50gx, and this is what, 14g. And this entire thing again will be divided by 1.4. So you get 50 divided by 1.4, which is 250 over 7. And 14 divided by 1.4 is 10g. This is 10g and plus 250 over 7 gx. I'm going to again break down the value for g. Which is 10 into 9.8 is 98, plus this one is 350x, right? Yeah, x. Yeah, 350x, right? So this is an expression for the tension at point Q using the value for x. Now, the questions are done. For part C, it says that hence justify. So hence find, justify your answer clearly the range of values of the tension which could occur in each row. Okay, the range of values means that obviously, as you can see that in between the value for P and Q, the value was 1.4, right? So the entire length for PX should not be greater than the distance of PQ, because we can clearly see on the diagram that X was in between the point P and Q, right? So it will basically not exceed the distance of P and Q. It should always be smaller than that distance. So if P and Q is 1.4, Px should always be 1.4. The maximum value Px could have is very close to 1.4, like maybe 1.39, 1.3955, like some real values like that. And another thing, as Px is a length, it could never be zero. For all lengths has to be greater than zero. That was the range that was provided over here, that x should be greater than 0 or less than 1.5. So in that case, the highest value or the lowest value the tensions could have for point P and Q, let's just find out. As your range of x was 1.4 and 0, right? So if I'm going to do the work for tension at point P, the lowest value, it could be, if the value for x was 0, in that case, TP would be 588 minus 350 multiplied with 0, which is going to be 388. Sorry, this is the highest value we're supposed to get, right? Yeah, this is the highest value. And again, for the lowest value, if you want to find out the lowest value, that is going to be for the value for x as 1.4, and TP in that case is going to be 588 minus 350, 1.4. That is 588, 350 minus 1.4, that is 98 degree, right? So in that case, TP can range between 588, it should be smaller than 588 or greater than 98. Okay. And then again, we're going to do the same calculation for TQ also. So for tension at point Q, highest value, that is x equals to 0, and TQ is 98 plus 3 multiplied with 0, which is only 98. So this is supposed to be the lowest value for this. Okay, wait 1 minute. So I'm just going to do this, keep this over here. And this is the lowest value. This is for the lowest value. because for TQ, we are adding the values. That's why for x equals to 0, you get the lowest value. For highest value, when x equals to 1.4, TQ is going to be 98 plus 350 multiplied with 1.4. This is again going to be, I think, 588. Right, 588. So in that case, same range for TQ also. TQ should be less than 588 and greater than 98. So these are the expressions of that potential at point P and Q could possibly have. After that, we're going to move to part D, where it says that given that the tension in rope attached to Q is 3 times the tension to rope attached to B, so P, we need to find the value for X. Okay, so Q is already 3 times greater than P. In order to make it equal over here, right, I'll obviously have to multiply 3 to the point of P because it is already smaller. For part D, if I want to make them equal, TP is equals to TQ. I already know that Q is 3 times greater, so I'm going to multiply 3 over here to make it equal. So it's going to be 3 multiplied with 588 minus 350x is equals to 588 plus, sorry, this is 98, 350x. So 388 multiplied 588 multiplied with 371764 350 is 1050x 98 350x. If I'm going to take every x together, 1050 plus 350 is 1400x and 1764 minus 98 is 1666. This divided by 1400, this is 1.19. The value for your x is 1.19. So the value for your d is 1.19. Px was 1.19. So yeah, that is it for your question. I think this was 5D, right? We will now move on to question 7 directly. Okay, so in question 7, part 1, we can see that a particle P of mass 0.5 kg is projected with speed 6 meters per second on a smooth horizontal surface. Over here, smooth indicates that the particle doesn't have any frictions over here involved towards a stationary particle Q of mass m kg. For particle Q, the mass is unknown and the velocity is 0. And after the particles collide, P has speed v and its velocity. So P has speed v in its original direction. That means originally P was traveling towards left, right? So after collision also, it was still traveling towards left, and Q has speed 1 meters per second more than P. That means V plus 1 in that case. We need to show this expression. Okay, so let me just draw the diagram that I think is probably correct for this situation. For particle 1, this is for before collision and after collision. I think This was 0.5 kg, right? This is mkg, this is particle q, and this is particle p. Okay, this was the scenario before collision, and if I'm going to copy this and take it to the left hand side, again, like I'm going to draw a similar diagram for the after collision journey also. In this case, both of them will travel in the same direction, as was already stated that after collision, P travel in its original direction and Q also travels in the same direction. And I'm going to consider that Q also travels in the same direction. And after collision, it has a velocity of V, and it now has a velocity 1 greater than the velocity of P. So it is going to be 1 plus V. So 1 plus V meters per second, and that is the case over here so far. So we're going to write the equation, the total momentum before and after collision. This is, by the way, for after collision journey. Okay, so I'm going to write total momentum before collision, total momentum after collision. Total momentum before collision was what? This for particle Q, it's entirely going to be 0, right? And for particle P, that's going to be 6 multiplied with 0.5 plus 0. And then after collision, it's going to be m multiplied with v plus 1 plus 0.5 v, which is 0.5 multiplied with 6 is easily 3. And this is mv plus m plus 0.5 V. So if I'm going to, in this case, what I'm trying to do is that I'm going to take this M to the, every V to one side and every M to the other side. Because in this case, we want to show V M plus 0.5 and then minus M plus 3, right? Okay. So yeah, I'm just going to take 3 minus M, and then on the left hand side, I'm going to be left with M plus 0.5 V. I'm going to flip it and make V the subject, which is M plus 0.5. I'm going to write minus V plus 3, right? This is exactly in the form of a question asked. So we have clearly shown this, right? That was only the working they were asking you. And yeah, this is it for part 1. For part 2, again, they have provided you with another scenario that Q and P are now projected towards each other with speed 4 and 2 respectively. Immediately after collision, the speed of Q is V and its direction of motion is unchanged, and P has speed 1 meters per second more than Q. We need to find another relationship between M and V in the form of this, where A and B are constants to be found. And using by solving these two equations, like this equation and this equation, we have to show that the mass of that object q was 0.9, and also find out the value for your velocity. Okay. Again, we have to do the same working over here. For part 2, I'm going to find out that before collision, after collision part. This is before collision. Portion where now they are both traveling towards each other. This is, I think, what? This is 4, this is 2. Okay. This is 4 meter per second, and this is 2 meters per second. And after collision, Q was traveling in the same direction. That means Q didn't change its direction. In that case, P must have reversed its direction, right? So this is v meters per second, and in that case, Q now have a velocity of v plus 1 meters per second. And this is for after collision. Yeah. Now, in this case, as multiple directions are involved, now you have to specifically say that I'm going to take direction towards right as positive or left as positive. Um, okay. So over here, I'm going to write that direction right, taking direction right as positive. Okay. So in that case, again, total momentum before collision must be equal to total momentum after collision, which is what? M multiplied with 4. This will be positive, but 0.5 multiplied with negative 2. And this will be what? mv plus 0.5 v plus 1. Let me just check for the last time if I'm correct. Q, V, direction P, 1. Yeah, that's correct. Okay. So we're going to start continue with the calculation. This is half with 2 is 1. So this is 1 and this is mv 0.5 m plus 0.5. So I'm going to take all the numbers to one side. So now you have, so this is 0.5 v, right? Yeah. So which is 4m minus 1 minus half, and then you have mv plus 0.5 v. Let me just go back and see in what format they were giving the answer. Okay, right. So in that case, I'm going to obviously flip it and make v the subject. Like I'm going to take v common from this side, which is v m plus 0.5, and on the other hand we have already 4m minus 1 0.5 is obviously minus 1.5, right? In your question this was written in the format of v m plus 0.5 am plus b. Now you can clearly see that the value for a must be 4 and b must be negative 1.5. So this was it in the format. We have clearly shown this. This is your equation 2, and the previous one we calculated, this was your equation 1. Now, it says that using these two equations, you have to find the value for m as 0.9 and hence find out the value for v also. So I just have to, substitute the equations over here. The work is still not done. We're going to write that from equation 1. I'm going to rearrange equation 1. So from 1, equation 1 was v m plus 0.5, I think. 0.5 minus m plus 3. Okay. M plus 0.5, and then I can write it as 3 minus m for my easiness. I'll just make v the subject and it will be 3 minus m over m plus 0.5. Now this is your equation third, right? I'm going to substitute this third equation into the second equation we calculated. So I'm going to write, let's just write from here, substitute this third equation into the second equation, which was v m plus 0.5. This is equals to, oh wait, 1 minute, vm plus 0.5 and then vm plus 0.5. Like if I just, wait 1 minute, I'm just making it more complicated. 1 minute. If I'm just going to write the two equations separately, for example, v m plus 0.5 minus m plus 3. This was your first equation, and the second equation we got was vm plus 0.5 4m minus 1.5. This is equation 2. We can clearly see that first equation is also a value for vm plus 0.5. Second equation is also a value for vm plus 0.5, right? So I can just substitute the two equations directly. Sorry. So I'm just going to write that substitute 1 into 2. In that case, I can just write minus m plus 3, 4m minus 1.5, which is 1.5 plus 3, 4m plus m. And that's going to be 5m. 1.5 plus 3 is 4.5. So 4.5 over 5 is 0.9. Right, so we got the value for mass as 0.9 as it was stated. So that is correct. And then again, we can just input this into any of the equation to find out the value of V. Sorry. So I'm just going to write substitute M 0.9 into equation 1. So we have V minus M plus 3 over M plus 0.5, which is minus 0.9 plus 3, 0.9 plus 0.5, minus 0.9 plus 3, 0.9 plus 0.5, which is 1.5 over here. So the velocity after the collision of particle P for scenario 1, velocity after the collision of a particle Q for scenario 2 was 1.5 actually. Right, so this is it for the final answer of question 6. I hope it was clear enough for all of you to understand. Yeah. Oh wait, this was separately for part 3, right? Like after this was it was question part 2, and from this part this is the question 3. Okay, right. So yeah, that's it for question 6. We're going to move to say question 7. We're going to move to question 8 quickly. Okay, now over here it says that at time t equals to 0, a football player kicks a ball from point A. Now over here, A is not as the origin, A is some distance away from the origin, right? Which has a position vector of 2i plus j and on a horizontal football field. And the motion of the ball is modeled as a particle moving horizontally with a constant velocity of this much. We need to find the like speed. So if we have the velocity, you just have to find out the modulus. So modulus can be easily calculated, which is 5 square, like I square plus j square, entire thing under a root. Okay, that's just it for modulus. If they have provided you the vector of the displacement, they want to find out the distance, you find the modulus of displacement. That will be distance. Okay, similarly over here also, they have provided you with the velocity, that is a vector quantity. You wanted to find out the speed, so just find out the modulus over here. It is 25 plus 64, that is root over 89, or approximately you can write 9.43. This was only the working for part A. It says again that the position vector of the particle after t seconds. Okay. Now, for this cases, I always draw a diagram that originally it was at origin, right? But the journey didn't start from the origin. The journey started from point A, which was 2i plus j meters away from the origin, right? This is where the journey started. And from this point, it starts traveling with a speed of 5j plus I. Sorry, I think 5j plus 8, so 5i plus 8j velocity, 5i plus 8j velocity. With this velocity, it was traveling for t seconds and it reached to this position, right? Whatever this point is, like I'm going to consider as this as a prime, and we need to find out the value for this from the origin to the a prime. We're trying to find out this O to a prime calculation. So let me just draw the diagrams, arrows over here. Now, as you can clearly see that from O to A and A to A prime, right? They're traveling in the same direction. How can I say that they're traveling in the same direction? Focus on here. I'm not picking up my pen from the screen as I'm moving from O to A to A prime, right? So if I do not need to pick up my pen from the screen for connecting two lines, they are obviously traveling in the same direction. I can connect O to A to A prime without picking up my pen from the screen. That means these two lines are traveling in the same direction. Whereas if I want to find out the direction for O to A prime, for this case, I have to pick up my pen from the screen. Right, you can see that from O to A prime, I do not pick up my pen from the screen. From A to A prime, this is an opposite direction. So in that case, lines in the same direction traveling, I'm going to write that as OA plus AA prime. This must be equals to OA prime. Right, so we're going to write OA prime is equals to OA was already what? 2I plus J, right? And A to A prime, we can find out the distance by multiplying the time into velocity, right? If you remember this equation, V is equals to dt, just have to make D the subject, which is D is equals to Vt. Yeah, they wanted to find out the velocity position vector after t seconds, right? So this plus O2, so this A to A prime is a product of this velocity and the velocity vector and time. So it is going to be 5I plus 8J multiplied with T. You can keep your answer in this format or you can also simplify it. I would always suggest simplify it further, which is going to be 2I, sorry, I'm going to consider like writing I together and J together. So 2 plus 5T, these are I components, coefficients, and then we have 1 plus 8T, these are J coefficients. Right, so this is an expression of the new position vector for the particle A. So for that ball at point A, which was originally at point A. Okay, this was all the work for part B, and it is done. Okay, so now we'll move on to part C. It says that point B on the field has position vector 10I plus 8J. Find a time when the ball is due north of B. Okay. For this, we need to draw a graph to have a better explanation or a better understanding. For example, this was your origin, right? And after A to A prime, this is where your ball is now present, A and A prime. Okay, and this is also point B. Like over here, this is also point B. Right, and it is also stated that point A prime is exactly due north of B. If point A prime is exactly due north of B, we can clearly see they are situated on the same x-axis, right? That means they are going to have the same value for I, but their J values are going to be different. I think we have already stated in some video previously that uh, I represents your x-axis and J represents your y-axis. So if after traveling that whatever distance, right, the particle is at point A prime and A prime is exactly due north of B. That means point like these 2 points are going to have the same I component because they are exactly in one straight line, right? They will have different J components, but they're supposed to have same I components. So I'm going to write it down as we're going to do the calculation for part C. At sorry, we're going to write that when, sorry, or we should write it as at time is equals to t seconds when ball was due north of B, point B, we're going to write they have same I coefficient. Okay, so in that case, for OA prime, I coefficient was 2 plus 5t, right? This was. In that case, I can write that I is equals to I, which is, I'm going to write 2 plus 5t. That will be equal to the I coefficient of point B, which was 10. Right? In that case, I'm going to write this is equals to 10, which is t equals to 10 minus 2 over 5. That is 5 over 8. So 8 over 5, which is 1.6. That means at time t equals to 1.6, ball was exactly due north of B. Right? This is the time. Okay. So that was the working for part B. We will do the working for part D. At time t equals to 0, another player starts running due north from B. Okay, the player starts from B and it would travel from B to reach that point, like meet that ball at north position and moves with constant velocity v. It is also stated that given that the player intersects with the ball. That means exactly the player will also be at that north of point B at exactly when time equals to 1.6 seconds, right? Because the player needs to hit the ball and the ball was exactly due north of B at 1.6 seconds. So they must be at the same position and when time is equals to 1.6. And we need to find the value for V over here. Okay. So it is exactly like this. The object is traveling from B to this A prime, and the object was already at A prime, right? So over here, their distances or vectors should all be equal to each other over here. And this is how the expression should be. And that for ball is equals to that player from that point B. Right, and how can you find out that from point B? Obviously, the player starts from point B, right? For the player, this is how the entire case is. This is the origin, right? The player was originally at point B, and after uh, some few seconds later, it is supposed to be at point A prime, right? It is going to beat the ball at point A prime, so obviously it will be at A prime. So we need to find out the value for O to A prime for the player this time. We're doing this for the player. We already have this 10I plus 7J. And from A to B, it was V multiplied with T. We already know from B to A prime, the player must travel this distance, B to A prime, within 1.6 seconds, right? In order to meet the ball. So it's going to be directly 1.6 multiplied with V. We need to find out the value for OA, which you can clearly see is the summation of OB and B to A prime. So it's just going to be OA prime, OB plus B to A prime, which is 10I plus 7J plus 1.6 V. And again over here, from B to A prime, right? This is exactly a vertical line. For vertical line, it is going to be exactly J because it's going to have a change in y-axis. It doesn't have any change in x-axis. So this is entirely a J component. So I'm just going to write 1.6 J, which I can clearly write it as better in this format, 10I plus 7 plus 1.6 V J component. Okay, now this is an entire expression for OA again. Now I got two expressions for OA, one for the ball, one for the player. I can obviously equivalent, make them equal to each other and use that expression to find out the value for V. So OA prime in terms of ball equals to OA prime in terms of the second player. Right. OA prime in terms of the ball was 2 plus 5 T I and then 1 plus 8 T J. I already know the value for T was 1.6. I'll write that later. 10I plus 7 plus 1.6 V J. I'm obviously not going to consider taking any values from I because I coefficients doesn't have V. I want to find out the value for V. V was in terms of J coefficients. So I'm just going to compare J coefficients over here. Comparing J coefficients, which is going to be 1 plus 8 multiplied with 1.6, the value for time, and then 7 plus 1.6 V, which is V is 1 plus 8, 1.6 minus 7 divided by 1.6. So 1 plus 8, 1.6 minus 7 over 1.6 is 4.25. So final velocity, which is the second player, was moving from point B to the north of point B in order to meet the ball, was 4.25 meters per second. Okay. Now after this, for the last part, for part E, right, it says that state one physical factor other than air resistance, which could be needed in a refinement of the model of the ball's motion to make the model more realistic. As this is a one mark, as I have already said that air resistance cannot be a possible answer. In that case, you can write that There could be a possible friction, which means that the second player or the first player also could not move with a constant velocity, right? They must either move with either acceleration or deceleration. So you can just write that friction between the player and the ground is present, or friction between the player and the ground should be taken into consideration. In that case, constant velocity could not be achieved by either of the players, right? That could be one of the possible answers. So I'm just going to write the answer over here, that friction should be taken into consideration. So constant velocity would not be achieved, right? This is one of the possible answers for part C. So sorry, for part E. Okay. Right. So yeah, this is it for your entire Mock 1 M1 solution. If there is any problem, obviously we will solve that in later classes. So far, thank you for watching the video.